indeed. All right, so we're starting now Module 2, so we're going to be reading through the first half, unless you've already read through the first half of Module 2. You may have done that already, okay? And we'll be looking at some basics of chemistry. All right, so chemistry has a lot to do with all the sciences. Biology has a lot in there, and, and of course chemistry itself and this kind of thing. So we're going to see chemistry being important in almost every one of the disciplines of science. So our first blanks we'll be filling in is matter. What is matter? You already know this. Matter is anything that takes up space, which is the same thing as volume, and has mass or weight for our purposes, seeing as how mass is going to be measured by a scale based on the gravitational pull of the Earth. Okay, we're not going to go outside of the Earth's atmosphere here to weigh anything. All right, so chemistry can be fun. You can mix things together and make things, change and bubble and explode and all this kind of stuff. I try to avoid explosions. Or at least, the fire alarms, right? So, it can be really fun. Today's experiments are not that fun, sorry. But next week, I'm going to add a new one next week that'll be a little better. And that's why I'm going to push one from next week to this week. All right, so we classify types of matter by their observable properties. So that blank is properties. So what are the properties of matter? So, let's go here. Let's look at this picture real quick. We can see it. The properties are the physical things. Okay, we can see it, like for instance, gold is shiny. Sometimes we can hear it. If you hit metal, it clanks. Okay. Sometimes we can feel it. It says here, I don't know, a rubber eraser, but I don't know. You can feel something soft. Touch, by the touch, it can feel cool. It can feel warm. Smell. Sometimes chemical reactions produce a smell, namely the chemistry that takes place in your kitchen. Okay, so cooking is chemistry. And that's changing stuff. And that smell, of course, is part of that physical property. And then we can measure things using things like thermometers, scales, stuff like that. All right, an example to consider is glass. Glass can be transparent, like our windows. We can see through them. We could have a dinner plate that's made of pottery type of glass, which you can't see through, so it's called opaque. So there are two types of glass, but they have a different physical property. So that's all that's trying to state right there. Okay, so sometimes, like for instance, you got the plastic tables are lighter weight than those tables in the. Do they have those tables here? Those really heavy ones that are made with that composite wood stuff. I don't know what it is, but it's very, very heavy. So they're both tables. They're both solid, but one's heavier than the other. That kind of thing. All right, we have those blanks filled in.
The glass is transparent.
What is that? Glass could also be translucent, like you have usually on a bathroom window, right? Light comes through, but you can't actually see through it. Okay, so matter is often called a substance, and there are two main kinds of substances we're going to consider today. One of them is a pure substance, and the other one's a mixture. All right, so this is a pure substance. It's showing a bowl of salt. So that bowl is filled with sodium chloride. It's sodium chloride all the way through. All right, so it's pure salt. A mixture would be something like your salad dressing. You have to shake it up, right? Because sometimes it comes apart. Because it's got oil and water, you shake it really well and it goes into this mixture. And you can see how it looks a little, different in one place versus another. Okay, and let's say we had coffee with sugar in it. That would be a mixture, even though it would look the same all the way through. When it doesn't look the same all the way through, we'll see what that's called. Okay, so our pure substances are made up of either an element or a compound. Okay, so what it means is that everything that's there is the same. For instance, I could have the element helium in a balloon, and my balloon would be floating. All right, it's a pure substance of helium. I could have a pure substance of oxygen in a hospital, like oxygen tank, and that usually travels around with two oxygens together, so it's O2. They like to go together because they share electrons that way. And so it's still pure, though, because it's nothing but oxygen. Josh?
What happens if you breathe in too much helium?
If you breathe in too much helium, okay, so I have to qualify this because it could be bad in the sense that if you went into a room and there was nothing but helium and you breathed it in, would you survive very long? Because you need oxygen, okay? But if you breathe it in, you suck it in, and you talk, it's really, really lightweight, and it rushes out of your lungs really fast, and that's why it makes your voice higher.
So you would or wouldn't survive?
If you were in a room that had nothing but helium, you would not survive because you need oxygen. Okay? And so I read a thing one time that said it's not a problem to suck in a helium balloon and do like that. But if you did it like 100 of them, your body might start to have an oxygen debt because it's, you're putting in too much helium instead of putting in oxygen. So our lungs are designed to breathe air, so we should breathe air, right? We should just stick with that. All right, so a compound would be something like water. So I can have pure water. For instance, I have a water filter at my house called a RO water filter, which stands for reverse osmosis. It takes everything out except the water. All of the chlorine, all of the whatever else might be in there. If there's anything big like bacteria, which are tiny, but compared to an ion, they're big. It'll take it, I'll have nothing but H2O, but it also takes out the minerals that are in water. There are naturally minerals in water that are good for you. So what I have to do is I have to put my water through the filter, then I have to add minerals back in so that my water's healthy for me. It's not good to drink completely pure water. But it's pure H2O. All right, it's got two things in there. It's got H's and O's in there, but it's pure H2O. That's a compound. All right, so an element consists of atoms, but compound consists of two or more elements that make a molecule. So a compound and molecule might be synonymous at this point. Yes, David?
So let's say you got a vacuum and you sucked all the oxygen in air out of a little box.
Okay.
And then you release some hydrogen and some oxygen. Would that just create water or?
Okay. It would have to depend on the. So I think technically we could say yes, you could do that. If you have hydrogens and waters, you can make. Hydrogens and oxygens, you can make water with that. But you have to make them attracted to one another because they are both gases, but yet we can see it in a liquid form, right, or a gaseous form, or a solid form, ice. Yeah, we'll be looking at some ice today. All right. So here's our elements again. Here's helium. Here's oxygen. Here's water. Here's our compounds. Okay. So they're both pure. Elements, compounds. What I don't want you to be confused of, because there's two of them, doesn't mean it's not an element. It's just two of the same thing. It's two oxygens. Hydrogens travel around together to H2. There's several, I2. Several that are called homonuclear diatomics. Yes.
So one of them's elements, one of them atoms. Aren't they both atoms?
They're all atoms, right. So like for instance, water is made up of the atoms of hydrogen and oxygen. Okay? And that makes a compound because it's two kinds of atoms. If it's just one kind of atom, oxygen, helium, then it is a element. Okay, elements are on the periodic chart of the elements as well. Okay, those are things we cannot make, but like David was saying, we could make water, right? We can make water. What's really easy to do is to take water and make it into the gases of hydrogen and oxygen. That's really easy to do. All I have to do is pass electricity through it, and that works. Or I did that with one of my classes today, my chemistry class today. All right, what about mixtures? We're looking at a glass of iced tea right there. A mixture may consist of elements, compounds, or both. It depends. All right, so iced tea is a good example of a mixture. I've got water, I've got tea, it looks like I have lemon, I've got ice. So if a mixture is homogeneous, homo just means the same. All right, that means everything throughout it is the same. All right, it has the same consistency. So the word I think you're writing down there is same. If it's heterogeneous, hetero means different. So it means that it has different consistency depending on where you take the sample. So let's look at our glass of iced tea over there. If I look at it, I can see, if I look at the bottom of the glass, I can just see iced tea, right? But here in the middle, I can see iced tea and ice. And at the top, I can see iced tea, ice, and a lemon wedge. You see, so it's not the same everywhere in the glass, is it? But let's say we take the lemon wedge out, we eat it, throw it in the trash. All the ice melts. Then what do I have in my glass? Watered down tea. And it looks the same on the bottom as it does on the top. That would be homogeneous. Do you get it? It's totally the same right there.
But it's not the same, because it has different things in it.
Well, not if the ice is melted and the lemon's gone. Then all my tea is exactly the same throughout. You know. I would say maybe we stirred it. We stirred it. Because it was kind of, you know what happens when you're, and soft drinks are that, I don't know if I drink soft drinks, but when the ice melts in there and they get all diluted, no good, yeah? But I don't mind tea though, when it does that. All right, so my homogeneous mixture has things mixed in here. all evenly. We're heterogeneous, so I could take a, look anywhere and I'd have the same chance of seeing that thing there. Where my heterogeneous, it's all kind of nilly-willy. We don't know where it is, okay? Oil and water is one of those. Soil, if you look at soil closely under a microscope or a dissecting scope, which some of you have done, you can see it's very heterogeneous. All sorts of crazy stuff, little rocks, little, bugs, stuff like that crawling around. In our homogeneous, right here, we can look at it from any particular spot. Like if we look at, it says there air. Air just, seems the same all the way around. Here on the earth, that is true. All right, so let's take a look at this. We have coffee, and the coffee can even have cream in it, and assuming that it's stirred up in there, maybe some sugar in there, but it's homogeneous. It's all the same all the way throughout. I take my first sip of coffee and my last sip of coffee, and except for the temperature, it had a little cooled off a little bit. It's going to be the same at the top as at the bottom of the glass. Josh?
Is coffee bad for you?
That's off topic.
It depends. Yeah, I caffeine makes you a little jittery. Some people have a bigger reaction to caffeine than other people. Some people like the caffeine because it keeps them awake. I've just given up coffee because it makes me jittery. So I decided I'll have it on Sunday so I don't fall asleep during the sermon at church. It keeps me awake, And it'll be my special treat. I also put cream and sugar in it, and that's not the best thing to put in your body first thing in the morning. Sugar, yeah. So, but see, it's the same all the way. But look at that bowl of cereal. I wish they had shown a bowl of cereal in the bowl, flakes, milk. I wish they were like raisins or something in there, so we could see even more change in there. Depending where I look, I could stick the spoon in there and get flakes and milk, or I could stick the spoon in just right and just get milk, right? Or maybe just get flakes if it's really full and very little milk, kind of a thing. So it's heterogeneous. It's different depending on where you're looking, where you're getting your sample from. All right, so you're supposed to guess these. Somebody else put this in there. Ready? Is milk homogeneous or heterogeneous?
Homogeneous.
Homo, it's the same all the way through, right? Anybody here drink raw milk?
No.
No.
Yeah, it's got to be shaken? No, shaken, stirred.
Shaken.
But if you don't shake it, it is different, isn't it? You have the stuff floating at the top, So if you shake it really well, raw milk,
I drink almond milk and it does that sometimes.
does it? Huh, I didn't know that.
Raw milk does that.
Let's say here for our second one about orange juice. Is orange juice homogeneous or heterogeneous? I'm going to put it this way. It's got pulp in it. So that's the only way it's going to be heterogeneous, or if it's got pulp in it. Some people don't like pulpy orange juice. Some people do.
We get the pulp.
It's like you're eating food with it.
Yeah.
It's got stuff to chew on. Pop. Do y'all say pop? I have
So-
sister-in-law in Michigan, and she calls it pap with that kind of accent. What kind of pap do you want? I'm like, huh? We call it Coke. I just call everything Coke. So is your Coke homogeneous or heterogeneous?
Heterogeneous, because it has the little particles, bubbles and stuff.
Okay,
like that.
I'll buy that.
Coke
You
would
think
be
the
green
bubbles
if
in
they
there?
put food coloring in it?
It would be what?
It'd be green.
Green? I thought it would just be clear.
No. It'd be green.
All right, so homogeneous mixtures, we can look at something that we call a solution. Okay, so we're back to our tea now. Do y'all like to put sugar in your tea?
Yeah. Yes.
Coffee?
Yes.
Lemonade?
That's what makes sweet tea sweet tea.
Yeah, actually, there's sweet tea and there's sweetened tea, and they're very different. Sweet tea, you have to put the sugar in while it's brewing. Did you know that? Yeah. and
No, I put
that'll-
it in before.
Yeah, well, before you heat it?
Yeah, before it brews.
Okay,
No,
yeah,
you
as
like-
long as you
you get
heat
the
the
pitcher.
sugar with the tea, then that's called sweet tea.
We get the pitcher, put the sugar in there, and then we let it brew.
Okay, yeah.
Well, you can
And
also
it changes
put
it chemically that way.
Sugar in it and then stir it.
As long as you're heating it, as long as the sugar gets heated is my point. Then it's sweet tea.
So it
If
basically
it's
just
if you
has
get
to be-
iced tea delivered to your table at the restaurant and you put sugar in, that's sweetened tea and it's different. Okay,
We never do-
sweet tea's better than sweetened tea in my opinion. Okay,
There's a-
I like tea though without any sweetening at all, just plain. But here we go. We have some water. We're gonna put some sugar in it. We're gonna stir it up, and we will have a solution of sugar water. What do we have in there? We have H2O, and we have C12H22O12. That's sucrose, or table sugar. All right, and it gets mixed in there, and it just if I showed it to you, in fact, I could show you a cup of salt water and say what's in here, and you say, well, it looks like water to me, but if it were salt water, could you tell? No.
I
What,
can tell.
what way could you tell?
Taste it.
Yeah, you could taste it. You could find out then. Same with sugar water, which would taste better than salt water.
Salt water's murkier.
Salt water's what?
Salt water's more dark.
Yeah, but not if I put a little bit in there, right? Okay, another property of matter is state, the state of matter. What state is it in? Is it a solid? Is it a liquid? Is it a gas?
Or is it in Florida?
All right, we're going to watch a video. Don't be upset with me. This sort of talks down to you just a little bit, but sorry.
Do you know what water, air, and rocks all have in common? They are made of matter. Matter is something that takes up space. Now, you might be wondering why they all look so different if they are made of the same thing. But the truth is that everything around you is made of matter, just in different shapes and forms. Matter is made of tiny particles called atoms. Matter can be grouped into three main states: solid, liquid, or gas. To figure out which state of matter something is in, we need to examine its properties. A property is the way that something is that we can measure. The physical properties we will look at to determine state of matter are shape, mass, and volume. Mass is the amount of matter in an object. Volume is how much space that matter takes up. Solids are easy to recognize. Rocks, apples, pencils, and plants are all examples of solid objects. A solid object has a definite shape that doesn't change when you move it or put it in a container. They also have a consistent mass and volume. This is because the atoms in a solid object are packed closely together, so they do not move around. A solid will change shape only if forced, for instance, if it is broken or smashed. If you look around, you can find many examples of solid objects.
No, I can't find it.
Liquid is the next state of matter. Liquids have a definite volume and mass, but they do not have a definite shape. The atoms in liquid are still close together, but unlike the atoms in a solid, they can move around. This allows the matter in a liquid to flow. Because liquids don't have their own shape, they take their shape from their containers. The same amount of liquid may look very different in a glass and spilled on the floor. You can find examples of liquids around you too. Water, milk, and juice are just some of the liquids you might find. The third state of matter is gas. Gases have a definite mass, but they do not have a definite shape or volume. Like liquids, gases take the shape of their containers. Unlike liquids, gases will spread out to completely fill the container they are in. If a gas is not in a container, it will keep spreading out indefinitely. This is because the atoms in a gas are farther apart than atoms in a solid or a liquid, and so they can move freely. The air you breathe is an example of a gas. You might have noticed that you can't really see air. Often, gases are invisible, but they are still there. There are many different types of gases in the Earth's atmosphere, like oxygen, nitrogen, carbon dioxide, helium, and water vapor. Sometimes matter can change from one state to another. Water is a very good example of this. When water is frozen into ice, it is a solid. When it melts back into water, it is a liquid. When water evaporates into water vapor, it becomes a gas. Matter in all its states is everywhere. See if you can find solids, liquids, and gases around you.
All right, so,
They missed two types of matter.
oh, we're getting to those. Yes.
I was saying, like, I wonder if a scientist come along and like change this whole concept of matter.
Sure. If there's something that comes along to disprove what I'm telling you, then we'll throw it out. But because we can't prove any.
Oh, it's something that happened, like now, like in our
In your
era.
lifetime, yeah.
We're like
That's
halfway
something.
through the school year, someone comes and changes like, it's a whole new thing now.
Yeah, so there's a few things that I feel like that I've changed because of new data. You know, I can't think of them right now, but okay. So we're going to do a density experiment today instead of next week. Okay, so I'm moving density to this week because it's a little more exciting than the one we're supposed to do this week, which is just atomic motion.
What is that?
Fusion. Oh, we've done it. It's hot versus cold. How quickly things travel. Yeah, it's kind of a bummer. Yeah. So, so what is density? What does density mean? It means how much stuff is crammed into a place. All right. So let's say I had a balloon, okay, and I blew it up with air, and I took a balloon just like it. Instead of putting air in it, I put water in it. They'd be the same size, but they would be quite different, wouldn't they? Okay, one would be, and that's because air is going to be less densely packed. Those molecules will be less densely packed inside that space versus the water that'll be, it's liquid, so they'll be pushed much closer together. So they'll be in there. And if I maybe put a solid in there, I can't think of a solid, plaster or something, but let's make it heavier, yeah. And that would have a certain amount of density.
What about like putty stuff?
Something like that, Have you ever seen those kind of balloons you can
Wait,
squish?
put
They have like.
a marble in it or something?
Yeah, but I'd like to fill it up so it's the same volume. I want it to look the same as the air and the water balloon, but filled with something solid. I just can't think of what that could be.
With like
Gold. We could put gold in there. Gold's very hot when you pour it, but let's assume the balloon can take the heat. Yeah. Did you have
with
something
like
there?
something like silly putty, would that be a solid or a liquid? Because it still moves.
It's a solid. Yeah, but it's a solid. It might be one of those non-Newtonian ones. But so density talks about how much stuff is in a space. So we can see here, we're going to see different layers here of liquids, but everything has density. So look here, for instance. This is a cup of water right here. I've got a sponge that's floating. I've got a piece of wood that's kind of floating, but it's deeper in the water, okay? And then I have a metal that's down at the bottom of the water, okay? So it depends on the density of those blocks of stuff. And so it turns out every single thing, like for instance, I can show you a mole, that's a measurement, of aluminum versus a mole of iron, and that has to be much bigger in aluminum because aluminum is less dense. Aluminum is much lighter weight. If I had the same exact of aluminum and iron would be much, much heavier.
Or a mole of moles.
A mole of moles, yeah, that'd be a lot of moles, okay. Density has a math equation. Are y'all supposed to write that one down? Equals mass over volume, mass divided by volume.
It's a solution on it.
So it's just, we do have math problems that are density, but I believe we do those math problems next week. But we're doing the density experiment this week. But it's okay,
Sinking soda.
because we're going to be looking at changes in phases next week too. So we talked about phases just now. So look here, I have the same size block, but this one's styrofoam and this one is metal. Does that make sense to you? Styrofoam takes up less space per square inch. Okay, so there's fewer atoms there. Does that make sense? You get it? So styrofoam would float where a chunk of metal would sink in water. Okay, just like that. They're same size though. They look like they're equal in volume, different in mass because of density. Okay, back to our properties. There's other states of matter include something called plasma and something called the Bose-Einstein condensate. So when I was growing up, while we knew about plasma was nothing except stars burning. That's what plasma was. But now we've been able to duplicate it in a laboratory by making stuff really hot, and now you have a plasma TV at home, right? Probably. That's plasma in there, man, and lightning is also plasma. That was around when I was a kid. The Bose-Einstein condensate, I don't think we had that when I was a kid, so that's something new that's come along. So plasma describes the state of matter at extreme high temperatures, like a star, like a sun burning, okay? And then the Bose-Einstein condensate describes matter at extremely cold temperatures, less than 273 degrees C. All right, so very, very cold. So it turns out when we heat up matter and when we cool matter down, they act differently. They get kind of strange. All right, so we're going to see how that strangeness looks here by watching a couple of videos. As long as you have your blanks all filled in. I have a huge notes here. My pictures are lightning, neon lights. NE stands for neon, by the way. That is an element. And when you shine electricity through it, it glows. This is a plasma globe. I should have brought that. I have that at home. And then something called bottom right, plasma trail from the space shuttle Atlantis. Huh.
Is that that cloud stuff?
I don't know. I can't tell what they're talking about.
Wait, what did it say?
It said something about a
Plasma trail.
plasma trail from the space shuttle Atlantis during re-entry. So is it like this thing?
Oh yeah, looks like it.
Because that, I think, might just be atmosphere. That
Yeah,
yellow.
that's
Yeah.
Does plasma stay plasma after it's being turned into plasma?
Let's watch a video about it. See if it answers that question for us.
Have you ever seen static electricity cause a spark of light? What is that spark? What about lightning, the northern lights, or the tail of a comet? All of those things and many others, in fact 99.9% of the universe, are made of plasma. Plasma is a state of matter, drastically different from the more familiar forms. Take ice, for example. Ice, a solid, melts to become water, a liquid, which, when heated, vaporizes into steam, a gas. Continued heating of the steam at a high enough temperature causes the water molecules in it to separate into freely roaming hydrogen and oxygen atoms. With a little more heat, the ionization process occurs, and the negatively charged electrons escape the atoms, leaving behind positively charged ions. This mixture of freely roaming negative and positive charges is plasma, and at a high enough temperature, any gas can be made into one.
Any guess?
These freely moving charged particles behave very differently from the particles in other types of matter. When a doorknob, a solid, has static electricity on it, it doesn't look or behave any differently. And with the exception of a compass or other magnetic object, we rarely see matter respond to a magnetic field. But put a plasma in an electric field or magnetic field, and you'll get a very different reaction. Because plasmas are charged, electric fields accelerate them, and magnetic fields steer them in circular orbits. And when the particles within a plasma collide, or are accelerated by electricity or magnetism, light is generated, which is what we see when we look at plasmas like the aurora borealis. Plasmas aren't just beautiful celestial phenomena, though. Imagine a tiny cube made of normal gas with a very high voltage across it. The resulting electric field pushes some of the electrons off the atoms and accelerates them to high speeds, causing the ionization of other atoms. Embedded impurities in the tiny cube of gas cause it to gain and release a precise amount of energy in the form of ultraviolet radiation. Attached to each tiny cube, a fluorescent material glows with a specific color when ultraviolet light at just the right intensity reaches it. Now, make a rectangle out of 1,000,000 of these tiny cubes, each separately controlled by sophisticated electronics. You may be looking at one now. This is called a plasma TV. Plasmas also have implications for healthcare. Plasma chemists create highly specific plasmas that can destroy or alter targeted chemicals, thereby killing pathogenic organisms on food or hospital surfaces. Plasmas are all around us, in forms that are both spectacular and practical. And in the future, plasma could be used to permanently rid landfills of their waste, efficiently remove toxins from our air and water, and provide us with a potentially unlimited supply of renewable, clean energy.
Pretty cool, huh? Yeah. So yeah, there's still lots and lots of research to be done with plasmas to figure out, how to utilize them to the best extent. What if matter is very, very cold, however? Okay, so we get a really, things start to slow down. So that plasma speeds up, it's really hot. Now we're gonna slow things down. All right, so this, I don't believe there's any sound on this one. It's gonna show how the condensation works. Oh, there's a little music. So, all right, so there's a higher temperature. Gas atoms can have their own energy, they can move around a lot. When they're bosons, they're allowed to have the same energy at the same time. When it cools down, the atoms slow down, their energy decreases. Because of their quantum nature, the atoms behave like waves. Very low temperature, the waves become large. Now they're able to, at the very same energy, in the same quantum state, they turn into that. A single collective quantum called the Bose-Einstein condensate. Alright. So definitely we're doing research on this. What I will tell you is that it was Einstein who postulated that. He thought if we got stuff really cold, it might do something like that. And it turns out he was right. He didn't ever see it, I don't think. This Bose guy came along and was able to bring things down and make it that cool. It's hard to cool things down. You know, in fact, I was just looking at something they're doing up in this International Space Station. They wanted to work with really cool temperatures. Now, do you know why it's easier to work with really cool temperatures when you're in space? Because the temperature of space is absolute zero, negative 473 degrees C. Very cold. It's very cold. And so they can stick it outside. They can just put it out the window or something. I don't know. They have some fancy thing that opens it to the outside and lets that cold in. Trying to make things cold down here. You know, we're lucky to have our air conditioner that makes things cool enough for us to be comfortable in here. All right. So what's happening with this matter? And that what I was telling you about that Bose condensate was that as it slows down, the energy is less and less, so they move less. That has to do with this kinetic theory of matter. Kinetics means to be moving, to be in motion. So it turns out everything's in motion. And the ancient Greeks thought that. They said, I think everything's moving all the time, and they were totally right about that. And what's happening is in the solid, they're just not moving very much. They're just kind of hitting up against each other, you know. So this solid right here, it seems perfectly solid. All those little atoms are moving. All their electrons are spinning around their orbits, and they're all kind of bumping into each other. But they're super close to it. We perceive it as being solid. A liquid, they're allowed to slip past each other like we did, and we saw that in the video, right? So they can move. We call that fluid, all right? And then the gas, of course, is just bouncing all over the place. And the gas is trying to get away from every other gas. It's very antisocial, gas atoms.
It's an introvert.
Yeah, they just want to see you, you know. So it's kind of like I usually use the example of somebody's going to make microwave popcorn in the kitchen. You know, a little time will go by and we're all like, oh, somebody's making popcorn. How do we know that? Because the gases that have that smell associated are moving away from the microwave. All right, and they're coming to all the corners of the building, and we can smell it. Then if somebody left it in too long and it's burning it, we'll know it. And we'll say, oh, somebody just burned the popcorn. And we know because all those gases are moving away, and they'll go try to fill the container being this building, it'll go out the door, it'll just be off into space. Nothing ever disappears, but it can drift off into space. All right, you got these? Due to its motion, kinetics is driven by the phase of the substance. Water's really good. If it's solid, we've cooled it down and really slowed it down, and it's solid. But it doesn't take much to leave it out on the table, and it just melts. But it does take a lot to boil it. It takes a lot to boil water. It's very difficult, in fact. Okay, we're going to do a matching. Y'all have this in your book, matching? Okay, we're going to say, what is solid, what is liquid, what is gas? We have molecules moving rapidly, molecules moving fluidly, and molecules barely moving at all. So which one do you think the solid one is?
The furthest one.
Barely moving at all.
So just draw your little arrow like that.
Barely.
Our liquid is
Molecules moving
fluidly, right over next to it, comme ça. And that leaves our gas to point all the way up there. Okay, so if your book has that, you're supposed to just draw those arrows, yeah? Not difficult stuff, I realize.
No, I'm-
So hard. I don't know how to draw
If this is on a
arrows.
quiz, will you be able to get it?
Yes.
I don't know. It's too
I
hard.
can't draw. I'm sorry.
Diffusion is the natural movement within gases and liquids that spread particles from an area of high concentration to low concentration. That's the popcorn smell coming from the kitchen where it's really smelling very concentrated, all the way to this room where it's low concentration. Gases are always moving away. Liquids are too. If I spilled water onto the floor, it would spread out onto the floor. It eventually would stop. And the reason is the nature of water. Water holds on to itself and it forms a little kind of a bubble, you know, and it would be gravity pulling it down. If I let a helium balloon go in this room, I untied it and let it go, it would go like that, and all the helium would just go into the air right here, right? And it would just dissipate, not disappear. So we can see these are little atoms just moving around. We do say that they're elastic. That means they bump against stuff and they bounce off. Boing. They hit each other. Collision theory, they call it. Collision. If they collide with one another, they can react with one another. All right, so here we can see putting liquid in water. This is our lab today. So we're supposed to do, put liquid in water. I mean, color in liquid.
Exciting.
Color in water. I guess one of them's cold, one of them's warm.
Exciting.
I don't know. But it's diffusion. If I leave it in there, it would, like, what if I put a sugar cube, which are hard to find, by the way, in a cup of water and just left it? What would
It
happen?
would dissolve.
Eventually, it would dissolve, and would it spread completely out through the entire glass? It would. Eventually, throughout the entire glass. And then we could taste it, and it would taste sweet. Okay, that's diffusion. That's happening right there. Another property of matter is it metal or non-metal? Metals are shiny. Usually, they conduct electricity. We will have an experiment with this soon. You know, I'm tempted to show you today, but another time I have to save it for another lab. That looks like copper over there. Turns out quite a few of the elements on the periodic chart of the elements are metals. You may not think of sodium as being a metal because we think of it as sodium chloride, which is salt. But we have sodium all by itself. It's a metal. It's sort of pliable. I can mold it a little bit, but if I throw it in water, it explodes. That's why I can't get it. They won't sell it to me.
What?
Can't get it. It's illegal. All right, we have these blanks filled in then?
Wait, what if you just find it?
Yeah, I guess it's not very easy to find. Because then you could use it for nefarious reasons. Non-metals usually appear dull and are not good conductors of electricity. So most metals conduct electricity well, namely copper. Some metals aren't as good.
You're talking like copper wires? Or
Copper wire is
Oh.
really, really good for conducting
I
electricity.
was about to say, like, Miss Lewis has some wires that we use for engineering, but I don't think the same ones.
Yeah, I have copper wire in here today, yeah, so it does conduct. Aluminum is not as good. It can conduct, but that's why we use copper in our homes, because it is really good at getting the electricity from one place to another. Non-metals would be things like oxygen. Oxygen doesn't conduct
If
electricity.
it did, we'd all be in trouble.
Yeah, I know. Well, it will combust, but yeah. Okay, so let's guess which ones are the metals and non-metals. Is gold a metal or non-metal? Metal. I will tell you, they tend to be shiny. And they also tend to be malleable. You know, that means you can bend them. Did you know you could bend gold?
That's why the Olympics.
We have to add stuff to gold. Otherwise, it would be bending all the time. Because I'm not going to say it's like clay, but it's almost like it's almost like clay. I mean, it's just not quite as malleable as
So
clay that we play with.
hard gold isn't.
Like it's 24 karat, that means it's got 24 parts gold, and then the other stuff is some other metal to make
So
it so
they
it's
put
not so.
24
Oh,
carats
it's not
inside
pure
of it to
gold.
make sure it doesn't move around too much.
Yeah. All right, there you go.
24 carats pure gold.
Say again?
24
Oh,
carats
shit,
pure gold.
Well, but it's not
Oh,
pure.
it's
It's
very
gold that's used
24
for.
carat.
No, like
This.
usually rings are made out of 14 karat.
Oh, is that what it is?
Yeah, it's 14 karat. My rings are 14 karat. And
Okay, so
I've
24
been
karat.
researching for it, but
Okay.
yeah, rings
Yeah,
are made.
that's cool.
I mean, I don't know.
I just
if
know
you
we
have
have-
something else. then, you
I
know.
will say gold is typically found in a gold ore. It's called a gold ore. And you have to get it away from the ore to get the gold out of it. Then you gotta add something to it to keep it from being malleable. So what about aluminum?
I believe that's a metal.
Is it a metal or non-metal?
Non-metal.
Oh, no,
It's
no.
actually a metal. It's shiny. It will conduct, I guess gold will conduct electricity. It's just not as good as copper. Wood,
No.
non-metal. Glass,
Oh.
non-metal. In fact, we use wood and glass to keep electricity from moving through stuff. It's called an insulator. Plastic is the best insulator. That's not going to conduct any electricity, and it's not very metallic, although I guess you could spray paint it, yeah. Copper,
Yes.
Yeah.
metal. Iron filings,
Yes.
that iron is metal. And chlorine, so I have some pictures. There's some iron filings. They happen to be magnetic. That looks like aluminum. And then we have chlorine. Like, I guess that's the kind of chlorine you put in your pool.
I don't think that'd be metal.
Not metal.
It's liquid.
Yeah. And if you were to look at a periodic chart of the elements, you would see all the metals are on the left side of the chart and all the non-metals are on the right side of the chart.
Wait, is chlorine considered like what chemicals go in that?
What chemicals what?
What chemicals go in chlorine?
Chlorine is an element.
Oh.
Chlorine is pure. It's a pure substance. An
Where do they
element
find it?
called chlorine. And you put it in your pool.
What do they find it, like little pockets of earth?
Oh, where do you find it? I'm guessing you mine it. Like other things. Yes.
Are there any elements that are liquids?
Yes. Did you mean metals that are liquids?
No, elements.
Elements that are liquids. Sure.
Chlorine.
Yeah.
Chlorine.
No, chlorine is
chlorine's a
actually
gas.
naturally a gas. And you have to do something to make it liquefy.
Yeah, it's a poison.
But I know
gas.
that one metal that's a liquid naturally on the earth is mercury.
Yeah.
But there's one called gallium. And so when I say, like if I put some gallium in my hand, it would just melt in my hand. Yeah, so it's not really a liquid, but it becomes a liquid very easily. So if it's, I mean, my hand, I guess my hand's 98.6, but in Texas it would be liquid, I'm guessing, in the summertime, kind of a thing. So I'm just trying to think of other elements that might be liquid, just naturally liquid. And it's not coming to my mind. Yeah, except mercury. That's the only one I can think of. All right, so this is the fusion at different temperatures. We're gonna do this, but I'm gonna have to go get some heated water. And we're gonna. This is your book. We're gonna write it up. It looks something like this. Does this? You have this in your book? In your lab book? With little cups and stuff
No,
on there?
it says
No.
Experiment 2.1, huh? We just have this, yeah, on the
Yeah.
left.
Oh,
Okay.
this is the additional lab page.
The additional lab page, they put that in there for me. We're gonna do density in that one. Okay, density's gonna look something like that. And then we're gonna be looking at the different densities. All right. And we're gonna draw up something like this. I don't know if these tables are in your textbook. And here are densities of common substances. Okay, so things that are heavier than other things. So if we look at things that have a big number, so I'm looking at, here's 19 gold. So this is density grams, so at 25 degrees, so the temperature makes a difference. And the density grams per cubic centimeter. So gold is 19.3, so it's gonna be heavier than mercury at 13.6. Do you see that? It's the same shape or the same amount of volume, but the gold's gonna be pretty heavy. And it makes sense, gold's a really big atom. It has a lot of protons in it. Look what's really lightweight. Oh wow, look at this one, 0.00009, hydrogen. Hydrogen's the lightest element we know. If we made a balloon out of hydrogen, it would float too. All right, except it would explode if it had a spark near it. So that's why we don't use hydrogen balloons. We use helium, they don't explode. What else is heavy? So these are the heaviest. Lead is pretty heavy. Silver, copper. See the metals, the really solid metals there. Look, aluminum's only 2.7.
Why is bone not one of the highest? It should be
Bone,
more
1.80, yeah. Well, we don't want our bones to be too heavy, you know. We don't want to be, we want to be able to move. Sugar, seawater, okay. Water, regular water, 1. Right? And then melting and boiling points. We'll do this next time. When things melt and when they boil. We'll talk about that next time. Okay, yes.
Well, it says seawater, like one of the bottom ones, but when you get deeper, it gets denser.
That's true. That's true. Because of if there's more salt, that would make it more dense, and if it's colder.
Yeah, like there's
So,
one guy
that's why it said it was all at 25 degrees C.
this one guy, he risked his life like scuba diving to the farthest depth he could go.
Oh, really?
Yeah.
Yeah, that's
He held the
hard
record,
on our
though.
bodies.
He held the record.
Yeah.
What about tungsten?
It's not on there? I don't know.
I believe the
I don't know tungsten, although I can tell you because I have a very fancy periodic chart of the elements in here somewhere.
The second edition
I believe
of
that's the
Social
name of
Science
what I'm
book has
thinking
one.
of.
Beginning.
See, I got a fancy one. I've got, this is what my students get, not as fancy a one. That's probably similar to what's in your book, right? Y'all have one in your book?
No.
No?
It's not in
Hmm.
the third edition.
Really? It might show up here pretty soon. So let's see where density is on this. They have everything on this chart, which is very nice. Planck's constants right there. Oh man, I have Avogadro's number, Boseman's constant. This would be a cheat sheet if I took this to my class in college. All right, yeah, so I don't know. One of these numbers tells what the, let's see, let's find gold.
Oh, I have a question.
Yes.
Is it true that like professors, like when they write the stuff, do they like write it and then like erase it right after, or do they give you time?
Some of them do.
Oh.
It just depends. Some of them are jerks. Some of them are really nice. Some of them let you record the lecture. All right, so I'm going to get stuff ready for our lab now. And I'm going to turn off this.
What if